Yeah. Yeah, so let's start today's lecture by revising a few concepts. So I introduced before you, I think you were present, flux of a vector field. So this is what that we look at last time. So how you define a vector field and how you calculate a flux through a surface. So for the sake of completeness, I would remind you, I said basically the vector field, you can assume a heat field that is flowing through some surface. Let's say you have a surface, something like this. And surface could be a surface of a some like three-dimensional, I mean, of course, it's a two-dimensional surface, but maybe it contains some volume, right? That's what the thing is. So the point was, let's say you have a temperature contour which was maintained in some temperatures, T1, T2, and so on. So you will see there's the amount of heat that flows through these slabs, I mean, through from higher temperature to the lower temperature. That's what it happens when you have a temperature gradient. So we said that you can calculate a quantity, and the quantity is something like this. So you can calculate a quantity, something like H through this surface, right? Something like this. And I put a surface integration over here, something like this, and which was just equivalent to writing a double integral and then defining this area in the respective, whatever the way you define a surface, right? For example, if we define surfaces in Cartesian systems, like for example, a book kind of shape, you can have a dx dy, but if you have a like circular surfaces, you can see, I mean, other things emerges. But I would just write down dA, current moment, and just what I mean is basically the surface integral is equivalent to a double integral, something like this. So what we were interested to see is that basically the aspects of the Gauss divergence theorem, that was our motto, and it was something like to connect basically this surface integral through a volume integral. So the idea was to show that, I said, I mean, you call this as a flux, right? I said flux. That means something is flowing out of this surface, and you can also write this integral something like this. So in book, you can also see, I mean, many books, they have a standard notation of like writing this, something like this. So where you will see now the dA vector has been has been separated in this directional part and his, the dA part separately. So direction will be something like, if I consider this surface, so direction will be always normal, something like normal coming out, right? So the best way to choose the normal direction is to take the basically your right hand rule and go along the surface, right? I mean, the way your surface is, you stretch your fingers and curl around the fingers, and you will see that the normal is the direction of your thumb. That's the way we take the conventional way of taking normal directions. So, but you can right now understand that basically this integral can be written as something like this. So this H vector, it has to be in the direction of normal, right, to survive, or for this integral is to survive, right? That's very obvious from here. So, we have seen that basically this can be written as something like integral over a volume, and you can always write down something like this, right? So this is your volume integral. So, so that's the way you can always write these things, and this is basically your famous Gauss divergence theorem, right? So the best way to check the applicability of this theorem is through some example, right? That's what the point was. And the first example that we considered is something like this. Example 1 was this. For example, I have a cube, which is something like this. Right, this was my cube. So there is some, okay, and let's say these are my x's of this. X's are, I mean, it's defined in the Cartesian frame, as you can see that the x's are labels x, y, and z way. So idea was to calculate the amount of flux, I mean, through this cube, and see that how this equation, if I say, let's say this is my equation 1, how the equation 1 can be satisfied, right? So that's what we try to look at it. And what I said, basically, I said you divide this cube into the various, the way I mean, breakouting surfaces, right? Because of the fact that you can see that you want to calculate this thing, right? I want to calculate this sort of thing. If I have a given vector field H. So I just want to calculate the dot product of H with the area vector, and the area vector will have some direction, right? And the direction will be the direction of normal. So I said, for example, if you consider this surface as a 1, this surface as a 2, and similar way, the upper one is 3, and the lower one is 4, and then this one is 5, and then the coming out one is something like 6. Right, so these you divide it into 6 surfaces, and then you calculate separately. So, so if you want to calculate through your, for example, through this surface, right? So let's say surface 1. So what will be the contribution from surface 1? So contribution from surface 1. So you remember what was the contribution from surface 1? How can you write? For example, if I want to write a integral something like h dot nda, right? So how can I write that thing in for surface 1? So surface 1, you notice that like surface 1 is defined as surface which is basically a surface in the basically y and z plane, right? So for this to survive, you see the area vector will be something like dy and dz, but this will have the direction of something like, what will be the direction of it? Can you say to me?
Along the positive x direction.
Yeah, I mean, but the normal will be something like this direction, right? So, and you choose origin somewhere here, right? So the direction will be like out from this book, something like this. So the normal direction will be out from it, and the positive direction is somewhere here, right? So the contribution will be effectively negative, right? So you can write something like Cx or Hx. I use C notation, I think, in previous, but let's keep that, for example, let me erase this. And just let's, for the sake of, I mean, the way I'm using my notations, H as a vector field. So let's keep it that way. So Hx, right? So this is my Hx, and which is not looking like Hx. Yeah, Hx. And then the limit of this integration will go from what? You remember how the limit of integration will go? Where is that? Yeah. So I said you consider this point as x, y, z. And then I said, if you move in this direction, what will be this displacement? You see, this is a very small cube, what we call infinitesimal cube, right? That's what it is. So that means the displacements are very infinitesimal in nature. That means they goes to 0 in some limit. So the point is basically this, I say this is a very infinitesimal displacement along the x direction. That means this is something like x plus delta x, y, and z. The coordinate of this point is, right? And what will be the coordinate of this point is something like x, y plus delta y, and z, right?
Z.
Z. And what will be the coordinate of this point is? X,
X, y, z plus delta z.
Z plus delta z. Perfect. Right. So then what you can do, you can just, because of the fact that now you have to integrate this integral, right? I said this is a integral in dy, and then again there will be integral something like this dz, right? And now you can take hx outside of this integral, and y will go from what? Y to y plus delta y, right? That's the way y goes, and this will be dy, and then z goes from z to z plus delta z, and this is something like dz. And now the final contribution comes as hx delta y and delta z. Is that okay? Let's say this is equation 3, right? So this was from this surface 1, right? Now, if you remember, I said there is a symmetry in this cube. For example, the contribution that you can calculate from this surface and the surface 1 and surface 2, they will be very much a similar contribution, except of the fact that the normal will be pointing here outward and normal will be pointing here something like this way. So if I have a vector field somewhere here on the cube, something like this, so the x component of this will be something that will be away from normal, but here the x, suppose if I have a field C here, the x component will be along the normal, right? So that shows that the basically contribution from 2 will be just opposite of the sign of the contribution of 1. So that's what you can do. Now, if I want to add the contribution from surface 2, right? So the contribution from surface 2 will be what exactly? So this you can write this equation hx. I can also I would say something like this. You write this for the sake of something that I'm just going to show you. So redefine this as equation 3 and cut this equation 3. So this is the first one. This is contribution from surface 1. Now coming to contribution from surface 2, I said this will be exactly equal to this, except of the fact that at surface 2, which is somewhere lying here, the way I'm making it. So this is displaced somewhere delta x distance, x plus delta x. This is displaced in x space, something like this. Other things are very much similar, except of the fact that normal is something pointing outward, right? So the contribution from this surface will be like if I have a field somewhere, something like this, hx, and this is defined at the point 2 here, somewhere, let's say defined on this location. So I have to take the component of this field at this surface. Basically, this is h field, and the component of h that will survive will be that one which is going to be in the direction of normal, right? So that will, hx will be surviving one. So hx2, and again delta y and delta z. This is equation number 4. So now I have said that to you that basically you see these are two equivalent contribution, except of the fact that hx is displaced. For example, the field that I have defined here, h have some magnitude over this surface, and h would have, h could have a magnitude over this surface. Only the fact is that delta x, a small amount of displacement I have traveled from one point by from moving from one point to another. So what I mean is that since delta x is very small, so you will see that hx2 and hx1, can I write this to be equal? I said I can write this to be equal in the limit of when delta x, I just put delta x 0. That's what they should coincide, right? If delta x goes to 0, they should just coincide. But if not goes to 0, but if it just exactly equal to 0, but however small delta x you choose, you can always write this field at point 2 in terms of point 1, and you will see that there is a change in that field hx2, which will be proportional to delta x, because of the fact that you have traveled this distance, and then the fact that how you basically change your hx field change with this displacement, right? That's the lowest order thing that you can write. There could be, of course, the other terms too. For example, I can write this displacement of delta x square and the term associated with this. But for the moment, I'm just very much interested to order of delta x. That's what it is. So this has some name in physics also. People write this called some sort of series expansion, and I'm just not very much, but for the sake of, I will just write, it's called Taylor series expansion. But let's not delve into those, big name right now for the moment, or at least for this derivation. So you vaguely know what I mean is particularly here, right? What I mean is basically the way you define the field at hx2, and the point is, for example, at this location 1 and this location 2, they will be separated by amount delta x, and that's why these two should not coincide exactly. So now if I say this is my equation 5, then now you can see that basically how you can write basically your contribution from 1 plus 2 is how much it was total. The contribution from 1 and 2 was something like I can write hx2 minus hx1, and then you can write delta y and delta z, right? That was your contribution. And then at the same time I said hx2 is how much? It will be something like hx1 plus delta hx by delta x, and then it will be proportional to delta x, right? So now if you just calculate hx2 minus hx1 from this equation, let's say this was equation I think this was 3 and this was 4. So now from equation 4, you can write hx2 minus hx1 is something like this, right? That's proportional to this thing. That's called equation 5. Now you plug equation 5 into equation 3, right? So what you get contribution from 1 and 2? The contribution from 1 and 2 will be something delta hx by delta x and delta x, delta y and delta z, right? So that's the idea, you see. And the similar way you can write down the contribution from 3 and 4, and then those contribution you properly name 3 and 4 accordingly. You can see the contribution will emerge as something like delta hy, delta y, and delta x, delta y, delta z. And similarly 5 and 6, you will see the contribution something delta x, delta y, and delta z, right? You name these equations 6, 7, and 8, right? And then you add all these 6, 7, 8. What you will get if you add 6, 7, 8? 6, 7, 8 adding will give you the what? This exactly, right? Total flux from your left hand side through this surface, and right hand side is what exactly? This is coming something like this, right? Hx by x and delta hy, y, and delta hz by delta z. And you see there's no integration sign, and this is just for infinitesimal volume delta v, right? So now you have to add all these infinitesimal volumes to sum up over total volume, right? That's the idea. So when you sum over this total volume, then what you can do, you can sum is equivalent to the limit of sum, right? That's what we talked about. So I mean, you integrate delta v, delta v, delta v, and so on, and add this, and which is effectively equivalent to delta hx by delta x, delta hy by delta y. I mean, this bracket is not required, plus delta hz by delta z, and this is dv, and this is over volume v, and this will be effectively equal to grad v, and this is dv, and this is basically your h, right? So we have seen basically, oh, my line has gone so bad. Let me correct that. This is very nice result. I just don't want to spoil it. Yeah, so what I mean is, so this was the famous Gauss divergence theorem. So what I said basically previous to you, that when we will try to look at the meaning of these terms, like for example, I said, when someone says to you, what do you mean by del dot v? And you say basically del dot p is something like divergence, divergence of a vector field, right? That's what the name is, vector field. But and you also give me the interpretation like something, for example, there is a charge, and charge produce electric field, and electric field is flowing out, and something like that. So something that is flowing out or flowing in, something like you spreading, something like that, where you can connect with the divergence. So you see that divergence is basically connected with exactly the amount, the flux that is passing through some surface, right? And the flux is, the field is basically normal to the surface. That's what the beauty is. So if you have a surface something like this, the flux is something like normal to, along the normal direction. So this H is along the normal direction, so that the flux is exactly equal to the something is related with the divergence, right? So you see that basically the divergence is something associated with the flux. It is, of course, developed in the context of liquids, but you will see that even it can be very easily generalized to the case of where you will see in electrodynamics and plenty of examples of it. I mean, we will also try to solve a few examples out of it, right? So now I would just, let me see if I have an example associated with it that I can put before you. So that would be nice. Yeah, so I just want to calculate to you, for example, you will see that the power, and I also mentioned a few things before you in the previous class, like these sort of in self, this, let me write again this. So for example, calculating this surface integral is equivalent to writing a volume integral, divergence of same vector field over a volume, right? This is my, let's say, the equation, right? This is 6. So now, for example, if I say to you, I have a vector field, something like H is given by R, right? You have a vector field, and so for this vector field, I want to calculate this surface integral. So I just want to calculate this surface integral for this given vector field. I don't know the surface and anything about it. I'm not specifying to you surface, but I'm just showing you the power of this theorem, that how easily you can at least some sense guess the answer for at least small vector, I mean simpler vector fields and things like that. And if I say, for example, my H is given by some vector R, so I just want to calculate this thing, R dot and ds. So can someone tell me answer? What will be the answer of this?
Sir, 3V.
Yeah, so how do you do that?
Sir, I have taken that dot product between del and H. Then
Yeah, so that's what you can easily see, that basically how easy it is to, I mean, you don't have to even look for a complicated surface or whatever the surface. I mean, for the sake of, I mean, you can always go in detail, and I think that you should check. I mean, once the surface is specified, right? For example, here I am not specifying any surface. So the best way you can do, you can calculate del dot R, and you notice that this is a constant, I mean, scalar. So once it is a scalar, it will always be a scalar, but it is not a function, scalar function. It is just a number, right? So once it is a number, once it is a scalar function, it is not as easy. You see my point. For example, if it turns out to be, for example, R is some complicated function, and del dot R turns out to be a scalar, some let's say some function, let's say 2x. So in that case, carrying out this integral, you have to carry out this integral. But here, for example, del dot R, this is not relevant to this, but I'm just pointing out. So del dot R, if it turns out to be 3, it is the right hand side is very easy, because you know that you have left whatever is volume V. I don't know what the surfaces are right now, and the surface will carry accordingly a volume. But since I know my del dot R, and my complexity has been reduced because of the fact that my operator has been taken care, and I don't have to bother about much. Only volume I know, whatever the surfaces may be, symmetrical surfaces, or mostly surfaces that you guys are going to encounter, they are very much symmetrical in nature. They are not going to very complex surfaces. They will be either I mean half circles, semicircles, spheres, or cylindrical surfaces. That's all. I mean, for you, these things are limited. So for this, these things can be volume accordingly to that surface, right? So that's what the answer is for you. So this is one example that you can see. Basically, this is example 2, let's say, because example 1 is for general case, where we have seen that this theorem holds for a surface, and the surface was basically your cubic surface, right? We have seen that for cubic surface, you can exactly calculate these through all this surface. I don't know what are the dimensions of cube and things like that. I have proved it for a general cube, right? So whenever a cube is given to you, whatever the dimensions of a cube is, you should be able to prove it, right? That's what I mean. I will give you a couple of problems where you can basically, for a general cube, you can I mean, not general cube I have proved that, but for a specified cube, let's say a cube of some dimensions is given to you and you have to calculate it. But for the moment, let's stop here for this discussion, because I have to prove a few more things to you. Let's look at few things. I said in the previous class that this is the basically divergence theorem. And there is something also associated with the curl, right? That's what. And I mean, let's also look at one more example that I find it's very important and essential for you, that to look into this. Let's say this is example 3, right? So what I mean is basically, I just want to write down to you basically a equation of heat flow for some specified condition. For example, I just want to show you the heat flow in some particular condition, and the condition is, for example, I have a box, I have a surface which encloses some volume V, right? And this is my surface. Let's say I have put all heat has been generated in the surface, and the all heat has been generated as a consequence of the fact that there has been a temperature gradient in this slab, and the temperature gradient has been setting up the flow of heat, and the heat has been set up, right? Let's say some heat has been set up. And now that since heat has been set up, so there is a heat field that is defined at each point of this surface. That's the way heat field is defined. Now, the point is, once the heat field is set up, and I say now you assume that there are no sources, right? I mean, what I mean by it, like, there is no additional way that you can now put the heat in the system. So in that case, what will happen naturally? You can think of that, since you have put some heat has been generated in the system, and since there are no other sources of heat in the system, the heat you will see that the heat will start flowing out of the system, right? And I just want to ask the question that how much heat is flowing out of the system? If there was total heat Q that was given in some volume, let's say this was some volume, small volume delta V. So let's say if Q is my heat per unit volume, so the total volume contains how much amount of heat? Total heat in the volume. What will be that amount? Can you guess that? If Q is the heat per unit volume and delta V is the volume, then the total heat in the volume delta V will be how much? So it will be something like Q delta V, right? Isn't it?
Sir, can you please repeat the question?
I said in this surface, inside this surface, let's say I have put a total heat Q. I mean, it's not total heat Q, but the heat per unit volume is Q, and the volume of the surface is, let's say here I define a unit volume and I put a heat Q inside it, right? And then I divide this entire surface in these small dx, 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 and on so on, and then I sum over all these surface. So what will be the total heat in the volume delta V? That's what my point was. If this was the unit volume, so heat per unit volume multiplied by total volume, so that will give you the total heat, right?
Yes, sir.
Right. So what my point was that since I have generated a heat and there is no additional heat that I'm putting it, if the heat has been generated, and now I just want to ask you that what will be my this vector field? I mean the way you calculated the flux of this vector field. So the flux is something like that is going to flow out of this surface, right? That's what you know about flux. Flux is something connected with the divergence, right? And the divergence is what? Divergence of this same field over this surface, right? That's what it is. We have proved that, right? So the flux will be this much through this surface, and if I, in other terms, I say Q is the entire, heat per unit volume in the total volume delta V, there will be heat Q delta V, right? So you can see from these two equations, equation 1 and equation 2, that what will be the net amount of change of heat that is happening. For example, rate of loss of heat, right? That's what it is happening, because you are not putting heat, you have just put heat in the box and heat is flowing out of the box. So there will be loss of heat, right? Because once there is some amount of heat has kept in the box and you are not maintaining it, the heat will lose with the surrounding, right? Body thandi ho jayegi, because of the fact that body will interact with your environment, and environment will have cooling effects on the body, and there will be flow of heat, right? So that's what we are trying to do. We trying to see that loss will be something like rate of change will be how much, something like how it is changing with the temperature, right? So the Q delta V was my total heat that was inside my volume that I have taken, this volume, right? I have taken this volume. I said Q is the heat per unit volume and delta V was the volume. So the total heat in this volume will be Q delta V, right? And I said, what will be the change of this total volume? So that change will be something like d by dt. You do that, right? That's what the way you determine change. And since there's a heat flowing out of the cell, there will be decrease in heat in this volume, right? So there will be a minus sign that will be the corresponding to decrease, right? That's what it is. And you see, this is also connected, and this is nothing but the change in the flux, right? And the flux is how much? Flux is something like this one, right? For a small volume. That's what we have derived. So now if you compare these two, what this gives you to, this gives something like the flux or the flow associated is something like rate of decrease in the heat, right? That's what it is. This is not dot. So this is, and this is a very famous law associated with the conservation theorems, right? What this called? Conservation of basically you can say energy, or even you will see that this is also called continuity equation and things like that. So the idea is basically the associated flux will decrease the total heat, and the amount of heat that is decreasing is equal to the way the flux is flowing out of the surface, right? This is a kind of conservation, right? Because of the fact that, I mean, something is flowing and the flow is associated with a decrease in the net volume, right? So this is basically a kind of conservation law that's very important for you. It will appear all the time. And you will see that you can also, basically see, now I put a homework for you. Derive the diffusion equation from it and read about it. Diffusion equation. So this is your homework, derive the diffusion equation. And how do you derive that? I'm going to tell you, because the heat will be what? Something like, heat will be something proportional to the temperature gradient, right? That's what I said. You have also seen, we have derived this thing, right? And let's say the proportionality constant in something like, here, let's say something like alpha delta T, right? Let's say that's the proportionality constant. So now, since this is the way heat is generating, now I just want you to plug this over here and generate diffusion equation, right? And also read about it. What do you mean by it? Read about it. That's your homework. Okay. So now let's look at some other concept. So the other concept that I just want to talk about is like circulation of a vector field. So we also want to look at the circulation around a vector field. So what I mean is basically, let's say you have a surface, something like this. This is a closed surface, right? Oh, sorry, this is a smooth surface. Always remember, there is no patch in the surface or anything. It's just that it has not been drawn even. I can also correct that. Not a big thing. So yeah, so try to generate a smooth surface always, because we are looking for smooth surfaces. For example, this is my surface. And I just want to now calculate some quantity, and that quantity is something, you have seen that, right? In the previous case, when I define a theorem for a gradient, right? I define, let's say you go from path 1 to 2, and you calculate a function, which is a vector function along this path. And let's say this is a line element ds. Now I just want to do a similar kind of exercise, but with a more general way, because you see, I'm generating a vector function here out of a scalar function, right? That's what you can see here. This was my vector function, let's say some f, which is a consequence of the fact that you have operated a vector operator on a scalar function and you have generated this function. But here the case is, for example, I have some general vector field. Let's say, for example, the way H is there, right? You have, let's say, a vector field H, right? And now I have again, let's say, line element from this going between these 2 points. Let's say this is something like ds, right? Now it was a similar kind of exercise the way you have done here in this case. And in this case, you are doing here. The only difference is that you are going around the loop here, but here the loop, it was just 2 endpoint was not joined here, right? That's what we have shown, that if you can join these 2 endpoint, what will happen, right? But here we have joined these 2 endpoint. And fortunately for our case, this H is some general vector field. Maybe it is not being generated out of something like this, right? The way it is written here. So I just want to calculate a quantity along this loop. And you see this circle in this basically integral is given to you the way textbooks writes to you, that you go along, you close the surface. When you travel along this surface, you close it, right? So we are closing about it around this surface. And let's say you travel along this surface gamma and just close this surface, and you just calculate this line integral. Maybe you have something like H. Let's say, let me take my. Yeah. So now what I mean is to calculate this line integral. And let's see what this turns out to be, right? For example, you know that how to calculate a flux, right? This will be something like not related with the flux, you see, because of the fact that you are taking a dot product of H dot ds, and which will be equivalent to something like moving a tangential component along this, right? Because of the fact that you can break it always in the normal and tangential parts, and you will see always tangential part will survive, normal part won't survive. And it's something like calculating this tangential part along this, and then tangential all along this. So it is something like the calculation with circulation, right? Something like circular in a circular fashion of vector field. You are calculating the contribution of a vector field along a line, you say, line element, and you are summing those line element along to making it as a closed loop, right? That's all the idea is, and it is effectively equivalent to a circulation, right? So will this be connected to some sense curl? That's the idea. Will this be connected to curl? So that's what we need to see it. Because of the fact that this is a normal intuition, right? And the intuition is telling you that it should be, because of the fact that you are integrating around this surface. And then once you are integrating around this surface, you are some sense curling around this surface, right? You are curling over. And once you are curling over, this quantity, some sense, should give you curl, right? So let's see how we can do that. So what I would say that you again prove this for you see, this is a line integral associated here. So it's a very, I would say compared to surface integral, it's a cheap integral, or even it's a simple integral. So if I have a surface something like this, let's say in YZ plane or XY plane, I have a surface something like this, right? Let's say this is my X coordinate and this is my Y coordinate. So can you prove this for a general surface something like this? Of course you can say something surface, because we are going along this line, we are going along this line, and we are going along this line, and that's the way we are going along close curve and tying this curve, closing this curve. It is not exactly we are calculating a surface integral, right? That's the point. So the point is, for example, I just want to calculate this thing. Let's say this integral along this. Let's say this is 1, this is 2, this is 3, and this is 4. That's what I just want to do it. So the similar fashion you have done it for cube, right? But you see here things are even much easier because of the fact that you don't have to. Of course, you can generalize it. You can take all aspects of it, but let's calculate for, let's say, at least this part. Then you will see what I mean by it. So I just want to calculate quantity, something like C dot along this entire loop, and I just want to calculate this integral, right, along this entire loop. So this will be effectively, let's say this is my vector field, something like this, which is defined as this, right? So along this, you will see that you can always break along the x direction. And let's say I have Cx, which is basically at this site, it has a 1 suffix that indicates that is along site, I mean this direction. So let's say this is Cx1, right? And then when you move from here to here, then C dot ds will be how much? So C dot ds will be something like, you see, it will come something like Cx1, and ds will be something like, you say this is dx, and you move from, let's say these are the point x, y, and you move from x plus delta x, and then y to y, right? That's what this is. And you will see that x moves from x to x plus delta x. So the total change will be how much? Cx1 and delta x, right? So along this one, right? This is the integral along this one. Now along this one, how much it will be? This will be something like how much? Now again, you can have a vector field something like this, right? You can again break it in component. This now along this direction, the component will be something like C by 2, right? And along this direction, the component will be something like how much? Something like perpendicular component, right? The way along x1, but this won't survive, right? The survival component will be this one. So that will be something like C by 2, and how much this will be? Delta y, right? Because of the fact that from here to here, the coordinate will be something like delta x. This will remain same, but y will change from y to delta y. Now, if you go from again here to here, you will see that this and this will contribute equally. Only the fact is that now the sign will reverse, right? So the along 1, this is along 1, this is along 2, and along 3 you can also have something like Cx3, right? Because similar way you can have C and you can break it Cx3, and then it is delta x, and then along 3, and now again Cx4, right? But that will again come with minus pi, Cy4 delta y, and that will be along this one, right? So now these are all equations. So that if you sum over all these things, you will get the total h dot ds, right? That's what you will total. And what it will be something? So it will be something, just wait. So this will be something like total C dot ds. This you go along 1 by 1, 1, 2, 3, 4, and you calculated Cx delta x. And this was, I put a suffix 1 here for along 1, then Cy2 delta y, and then Cx3 delta x, and then Cy4 delta y, right? That's what the total contribution is. And now you notice one thing, that since this was my loop, right? Something like this. So here I said this is Cx1 and this is Cx3. Now going from Cx3 to Cx1, how much change Cx3 brings, right? You will notice the change will be something proportional to delta y, because in this direction you are only traveling delta y, right? So the change will proportional to delta y, and how this Cx change with y, right? That's what the total change will be at, of course, this order, right? That's what it will be. So now if I calculate Cx3 minus Cx1 from this equation, let's say this is my equation, let's say 7, I think this is 7 number equation, this is 8. So now if I calculate from 8 to this, I can write Cx3 minus Cx1 will be proportional to something like this. And I can plug this expression over here. Now let's say this is 9. Plug 9 into 7, right? What you get? You get Cx1 minus Cx3 delta x. Similar way, you can write Cy2 minus Cy4 delta y. And what is this thing? This thing is delta y, and then of course delta x, delta Cx by how much? Delta y, right? And the similar thing will be this one. How much will be? You will see here only x will replace with y. So something like delta Cy by delta x, right? That's what. But there will come some minus sign, right? That's what the point is. So the minus sign will be Cx1 minus Cx3. Yeah, there is a minus sign, right? I think I have missed that. Here it's a Cx1 minus Cx3, and there is a minus sign here. And this is a plus sign. So this is delta x, delta y. So how you can write this equation? You can write this equation as something delta x, delta y, and delta Cy by delta x minus delta Cx by how much this is total? This is total delta Cy by delta x minus delta Cx by delta y and delta x, delta y. So you see, this is what? This is del cross C, and this is what? Z component, right? Right? And this is what? Area, right? So this is what? This is perpendicular to this one, right? That's the point is. So you can always write this del cross C, and then you can put a normal to delta A and then define delta A, or maybe dAu, right? That's even better. So this is over surface, right? Surface S. And this is connected with the line, right? So you are calculating this with the line, and then you notice that something like this. You connect a line integral to a surface integral, something like this. So whenever you have given a surface integral to calculate something like this, you can go through a line one, which will be a simpler one to calculate. Right? That's what the point is. Whenever you have given a volume integral, maybe if calculating volume integral is difficult, you can calculate surface integral. That's what the divergence theorem, right? So this is basically your Stokes theorem. Stokes theorem. Right. So this is this was saying something, right? Because of the fact that you see the line integral along a closed path is connected with the circulation, right? That's the point is. So you see the circulation is connected with the curl. So the curl is always connected with the circulation, right? That's what the point is. So these, I think that's conclude very important theorems of your vector calculus. And I think now we have to, I think a few more, maybe coordinate system I can introduce in the next class. And then of course, problem sessions are important to do with these theorems. But formulation wise, I think I have done everything to you. You know now how to derive these. And by the way, these are not any fundamental derivations. These are some sense connected with, for example, a particular geometry, right? And this is basically a squaric geometry is given here, right, in the XY plane. So this is, of course, a kind of examples. They are not something like very formalism kind of stuff. They are always example. You can see that with of course, with such general cases. I mean, you can always prove those things. It is true for any, surface, but depends upon the how complicated the surface is, so that you can calculate those integrals. So with that, I would say right now I just want to pause it over here for today's case. I think, and then next class we will see some problems, and we will try to find vector things in the next class with some problems. Of course, mostly try to look at those problems. And then we will start some other topic in mathematical physics, right? Okay. So I think I will stop here. Thank you. Yeah, so any question, Rupa, anything you just want to know, or your comments, anything, what you understand or not? Yeah, if you don't have, I think we will wind it here. Okay.